Welcome to another fabulous day in Calculus 3. And we are going to do surface and flux integrals today. Yay! So good news, you already know how to do an easy peasy surface integral. That's right. I already taught you how to do that in a previous module. We will revisit it. We'll review it just in case you forgot. And then we'll go ahead and do the more advanced surface integrals. Okay, so that's the plan. But first, some review. So far you should know that line integrals are evaluated along, we'd like to say lines, but it's actually curves, which may or may not be a straight line. Double integrals are typically defined on plane regions, but not all. Triple integrals are typically defined on solids. So that's something you should know. So the notation, here's a line integral right here. I'll just put a scalar one here that looks like that. A double integral might look something like this. So you've got that region here. And then triple integrals look like this. And you've got the volume element there. Okay. So what we're going to look at is integrals over a surface, which is different than any of these three here. Integrals over a surface, it's different. So let's do the review right now. Surface area. We did this already. I even did a whole proof on this and developed it for you. But here's the deal. If you've got a surface represented by z equals fxy, and you've got continuous partial derivatives on a closed region R in the xy plane, then the area of the surface, S, is given by this surface integral. So notice there's an S down there, and this ds is representing the surface area element. And you can't integrate that. You have to turn it into a regular double integral over a region. So the way you do that is you change the S to an R here. And then the surface area element is this whole huge thing here. It includes that big old radical with a 1 plus the square of the first partial of f with respect to x plus the square of the first partial of f with respect to y. That's called the surface area element. So that's your ds. And we did this already. So a little picture here. If you had, say, a capping surface, I'll just keep it sort of easy here. Let's say you had some sort of surface here, capping, and it was given by z equals fxy. You're trying to find the surface area of that capping surface over the projection of that surface, or they may give you the region R also, onto the xy plane. Okay, so that's what this is. It'll get you the surface area. Now we're going to use this knowledge to help us define the mass of this capping surface. So if they gave you a density function for that capping surface, so here's the density function, and we're going to change some of our notation. This is where it gets a little confusing, and I apologize, but we're going to change our f to a g. What? Yeah, we first had our capping surface represented by fxy. So if you don't mind, we're going to change that f to a g. Well, how come? Just because we have another f in the mix here, we're going to reserve the f for the density function. So the surface is going to be represented by a g instead of an f. And you want to make sure that you are clear about the distinction between f and g. If you confuse these on a quiz or exam, well, there's no more quizzes, but on an exam, I can't give any credit. Okay, because if you're lost and confused that way, then there's a problem. So here is your first big old surface integral that's advanced. I claim you already know how to do a baby surface integral. That's this right here. This is a baby surface integral where the integrand is a 1. And it by itself, it represents the surface area of your surface. So if you're going to find the mass, and that would be the best application of what we're about to do, it would be a double integral over the surface S, and you would put your density function here in the integrand, and then you'd have your ds. Now, that's not integrable, so you're going to have to change it or convert it to a regular double integral. So the regular double integral is going to be over some region R in the xy plane. The ds, remember, is your surface area element. That's that big old radical. It's pretty hellacious. So it will be, it'll almost look like this here, but remember we changed the f's for g's. So it's going to look like 1 plus partial with respect to x of g squared plus the partial of g with respect to y squared, and then your area, dA. Now, what about this fxyz? Okay, well, you're going to copy it down, but there's one little caveat about copying it down. Don't copy it all the way down. I'm going to do this first, but don't write this down yet. This is a problem because if your density function has the letter z in it, if it's a function that has x's, y's, and z's, we have a problem because remember dA represents dy dx or dx dy. There's no dz here. This is not a triple integral. Don't get confused. Don't all of a sudden go, oh, well, we'll have a triple integral. Surface integrals are double integrals, not triple. So what you're going to need to do is you're going to need to replace any z's that occur. And if you're lucky, you may get a density function that doesn't even have a z in it. So you're like, then just copy it down. But if you do have any z's in there, you need to replace the z with the capping surface function so that it's back to only x's and y's. Then you hope that this is integrable, because sometimes it's not if you have a big old yucky radical and you don't want to do any trig sub or anything. Okay. Now I'm going to point out some common student errors before we even do any examples. And these are so common. Let me just, please be careful. Because on your final, I'm going to give you a surface integral and it's going to be worth half a letter grade. So if you bomb that one problem on your final, boom, you just lost a half a letter grade on your whole exam. So that's not going to be fun. So one of the student errors is the one that I just sort of mentioned here. They forget to replace z in the density function with the capping surface function. And you want to do that. And I'm calling it little g here as well as in this theorem. So replace it. We'll do some examples here in a moment. The other big issue that I've seen students when they blow this problem is when they're doing the partials here in this big old radical, that's the surface area element, they accidentally take the partial of the density function f and stick it in there. So that's big no-no. That's going to be minus half a letter grade. I can't even give you partial credit for that because you're blowing it all the way, okay? So they accidentally use the fxyz partial derivatives when they are supposed to use the capping surface partial derivatives. Okay, so don't blow that. There's two big issues that can happen, and if you get lucky enough to get the right answer, well, that's nice, but you know, I don't give credit for that. Capping surface partials. Okay, so those are the two student errors that I've seen when I grade the papers. So now let's do a couple examples here of real life surface integrals. Now, when you're doing a surface integral like this, this scalar surface integral, kind of like the scalar line integrals, the best application I can tell you is mass. So the scalar line integrals, we were doing mass of a wire, but the scalar surface integrals, you're doing mass of a surface, a capping surface, okay? And no vector fields are involved, just like no vector fields are involved when we're doing one of those scalar line integrals. So are we going to do any surface integrals that involve vector fields? Oh yeah, we are today. Don't worry, it's coming. Oh yeah. Okay. So here's a problem that could be what I put on your midterm or your final. Just like this. Well, maybe change some of the letters or numbers, but very similar. So the first octant portion of the plane. So this is your capping surface. And they didn't give it to us in a nice way. So that's your job. You got to do something now. If I were you, I'd get it immediately. Solve for z. And this isn't too hard, you know, subtract the 2x and the y from both sides, divide both sides by 2. And this is your little g in the theorem on the previous page. That's the little g. This right here is the density function. So in the previous theorem, this is the f x, y, z. So if you look at the theorem up here, so you don't lose track of the f and the g and get all confused and accidentally swap them, the f stays there, okay? And then we're going to have this big old surface area element. Oof, that looks terrible. I know. Let's put that together now because it's a good idea. Since we have the z, let's go ahead and get the partials. Okay, so we know we're going to have the half, and then multiplying that by the derivative with respect to x, looks like I'm going to have a -2, and then simplify this, I get a -1. Ooh, that's nice. And then the partial with respect to y, I have that 1/2 there, and then I have a -1, so I have -1/2. Okay, do I always get constants when I'm finding these partials? Oh, no. It's definitely possible that you could get x's and y's in here, and oh yeah. Now we're kind of lucky here because this ds, which represents the surface area element, if you want to impress me on a quiz or an exam, actually use this vocabulary for me. It'll warm my heart, and I'll get that you really understand what's going on. This is going to be that big old, you know, radical with the sum of the squares of the partials, and then your dA. So for us, this is going to look like, not going to be too bad. We've got the -1 squared plus the -1/2 squared. And, you know, what do we get here? Oh, okay, 1 + 1 plus 1/4. Ha! Okay, what's 2 1/4? I think that's going to be 9/4. And that's the same as square root of 9 over square root of 4. And we actually get a constant, which is really nice. Now, does that always happen? No. But it makes this a lot nicer. Now, if I were to graph the surface, the capping surface, they said it's the portion of the plane in the first octant. Okay, you guys all know about that first octant. You know how to graph planes. You know, get your x-intercept by setting y and z equal to 0. So I get a 3. Then I'll have a 6 here for the y-intercept, and then I'll have a 3 also for the z. So here's the capping surface right here. This is the surface that we're integrating the surface integral over, the triangular portion of the plane. Oh, okay, fine. So now what do we do? Well, it's now time to look at this surface integral and start converting it to a regular double integral, okay? So what are we saying? We're saying that this surface integral, this s y squared plus 2yz ds, is going to turn into a double integral over the region. We're going to figure out what that region is here in a moment. Okay, and you're going to have y squared plus 2y, and you need to replace this z with what? Anybody know? Because you're not allowed to have z's in a...
Is it 6 minus 2x minus y over 2?
Mm-hmm. Yep. And put that in there. Oh man, that's messy. I know. You'll be able to cancel some stuff like that. And I haven't chosen an order of integration yet. So what is the region R? What does this look like in the XY plane? If you look at the trace that this capping surface makes in the first octant here, ooh, as we, I hope that you can appreciate that it's going to look like a triangular region. Not going to do anything there. There we go. It's going to look like the triangular region there in the XY plane right here, this region R. That's your region R. So how do you get that? Well, this line here, if you set z equal to 0, you'll be able to see the trace that the plane makes. So if you set z equal to 0 in the plane equation, you'll get 2x plus y plus 2 times 0 equals 6. So you get 2x plus y equals 6. And if you solve for y, it looks like you're going to get a diagonal line that looks like this. And we're in the first quadrant, since they told us we're in the first octant. So this is the region R that we are integrating on, okay? So now you can choose your order of integration. My personal favorite is dy dx. So I'm going to stick to that. I'm also going to reduce these 2's a little bit. And if you don't mind, I'm going to distribute the y over the parentheses all at the same time, okay? So then I will get what? I'll get y squared plus 6y minus 2xy minus y squared. And then I have dy dx. Hey, these y squareds end up canceling. Oh, cool. And then if you look at what x is doing here, pure number to pure number, that's 0 to 3. And y, don't do 0 to 6. That's not okay for the y. You're going to put a little man in there. And you're going to notice that his head, the upper limit for y, is on that diagonal line. And that has the equation y equals 6 minus 2x. So that's going to go there. And the little man's feet are firmly planted on the x-axis, which has the equation y equals 0. So there we go. And if you get this far, I mean, you're almost there, right? Now it's really easy to integrate the 6y minus 2xy with respect to y. And I get 3y squared minus xy squared. And you're going to evaluate between those limits. And this is always fun. Wow, that was terrible. So at this point, you could FOIL or, do any number of things. One thing you could do is factor out a 2, and then you'll get 3 minus x squared. So that really is looking like 4 3 minus x squared. Same with this. You got 3 times 4 3 minus x squared. Why am I doing this? Like, oh, that doesn't look good. Just because you can combine like terms, So now I got an x here, right? Make that look good. 12. Well, if I factor out the 4 all the way, this is really cool. Watch what happens. A little bit of fun with algebra. I'm not doing anything exciting here, but I want you to notice that there's a 3 minus x squared that's common to both. And so if I pull that out, the other factor is 3 minus x. So I really have 4 times 3 minus x cubed. And then I can just do a little bit of u sub, here and finish it up. It's not that hard. I'll just say et cetera, et cetera. And if you want, you can go use your graphing calculator at this point when you get to the single integral. And I get 243 halves. And that would be the mass of that capping surface, which is just a portion of a plane in the first octave. Okay? So that's your first surface integral. And it's not too hard, but it does require that you have all the ingredients and you're able to identify all of the ingredients. Okay, so it looks like I forgot something. I forgot my 3 halves when I set this all up. Yeah, that needs to go here. That needs to go here. That needs to go here. I have it in my notes, but of course I just totally spaced. And then you'll end up getting the 243 halves. If you forget that, you'll forget, and then you won't get it right. Yeah. Thank you for pointing that out. My mistake. Got to have your DS, your surface area element in there. Okay, so that concludes example 1. Now let's do a little bit tougher of a problem because it's going to turn out the DS takes a little bit of work, but you've seen something like this before when we did some other fun and play with these kinds of integrals with algebra. It's just algebra. So how do I know that's a surface integral? Well, look at the S. That means surface integral. Do you see an S there? That's a dead giveaway. You got a surface integral, and then you got the ds, and that's that big old radical. So what do we have here? This is the surface. It's a portion of a cone that lies between z equals 1 and z equals 4. So it actually kind of looks like a little bit like a funnel right there. It's a piece of a cone. So that's the capping surface. So you want to try to solve for z because you need your g. So if you do that, you'll get plus or minus the square root of x squared plus y squared. And because we're looking at the portion of the cone above the xy plane, we take the positive. And then I'm going to need to do partials because this is our little g. And so it's going to take a little bit of work here. So let's go get the little gx and the little gy. So we're going to use the chain rule, you know. So how do we do that? You're going to get a half x squared plus y squared to the negative a half times 2x, and then rewrite this, simplifying, the 2's cancel, and I'm going to put the radical back in. You can do a similar thing when you're getting the other partial. So this time you're differentiating with respect to y. So after I cancel the 2's, rewrite this with positive exponents, I can put my square root back in. Great. Now what? Well, you got to do your ds here. So you're going to have this whole radical, you know, and it's going to be kind of a mess. But good news, the algebra will save us. It'll simplify really nice. That doesn't always happen, but if it does, it's great. I'm happy. So check this out. This looks like a nightmare, doesn't it? It's like, oh man, that looks like a horrible looking surface area element. Like, what am I going to do with that? Will that ever look better? Oh my God. Well, yeah. If you use the fact that when you square a radical, the radical goes away. So that's a nice thing. And then if you use the fact that you can add all these terms together, if you could get an LCD, a common denominator. And so if you change that 1 by multiplying the numerator and denominator of 1 by the LCD, then it turns out you can add all 3 of these fractions together because they all have a common denominator. Yay. So keep the denominator the same and then add up all those numerators together. And then what do you notice? Do you notice that you can combine like terms? You got 2 of those x squareds and you got 2 y squareds. But then you can factor out a 2 from the numerator, and wow, this whole thing is going to reduce really nice. And you'll just end up with the square root of 2. And you'll still have this dA here. That's part of the surface area element. And you'll figure out if you want to do, you know, dy dx or dx dy. It's up to you. But here's the problem. We got our capping surface, which is like a portion of this cone here. And they gave us a density function. This right here is the f x, y, z. And notice it does have a z in it. So we're going to have to replace the z with what? This. We're going to have to replace. Okay. So what do we have so far? So this surface integral that we're working on right here, that currently when you write it like this, there's your original, you're going to replace this with the square root of x squared plus y squared. Oh man, that looks terrible. But then the ds was just a constant. Okay, that's not too bad. And now it's like, well, what's the region that we're integrating over? What's the R? And they didn't tell us anything about that. And this capping surface never touches the XY plane. So you can't set z equal to 0 and go, oh, well, what's the trace? Because there is none. Like that, you'll get an equation that has no solutions. You'll notice this capping surface is hovering above the XY plane. So instead of seeing what the trace is, you're going to have to see what the shadow is, the projection of this surface onto the XY plane. And it's going to turn out to look like concentric circles. But what concentric circles? So this is the projection of S onto the XY plane. So what the heck? So remember that they're saying Z could equal 1, and then also Z could be equal to 4. So what does that give us? So if I take the capping surface, which was given to us, like this is the cone equation right here. That's our cone equation, the way they handed it to us. And when Z equals 1, if I substitute, it looks like that is going to give me a circle of radius 1. And if I substitute Z equals 4, I'm going to get a circle of radius 4. Oh, so this is going to look like a donut. You're going to have the region R is going to look like this nice donut, concentric circles. And you guys know what we're going to have to do, right? Convert to polar. Oh, yeah. You're going to need to. So R is going between 1 and 4, and theta is going between 0 and 2 pi. So all the things that you've learned in the last 2 months are needed for this problem. Like, wow, this is like a triple whammy problem. You got all sorts of things going on here. So when we're looking at this regular double integral, the region was the donut, and now we're going to start replacing things. So we'll keep the square root of 2 out front. We are having theta go between 0 and 2 pi. R is going from 1 to 4. And now let's start doing some more conversions. X squared converts to R squared cos squared theta. The square root of x squared plus y squared, that converts to just an R. And we already took care of the square root of 2. And then dA, be a pirate, R, dr d theta. Oh my God, this is a mess. So we got to keep going. Notice that we have a whole bunch of R's in there. So what would be wise if we combine all of our R's in a single power of R before we integrate with respect to R, okay? And then the antiderivative of R to the 4th is R to the 5th over 5, and we'll evaluate between 1 and 4. This is not going to be pretty, okay, people? Like, it's going to be gross. And as usual, I'm running out of paper. So what do we have here? I think this is 1,024 fifths minus 1/5. That's 1,023 fifths. I know, weird, huh? And that's just a constant, so I'm just going to pull it out in front of the integral, and then I still have that square root of 2. And then how do I integrate cos squared? Anybody remember from this last module when we would have a cos squared to deal with? What do?
Power reduction formula.
Power reduction formula. Very good. Yep, you're going to use it. Power reduction formula. You think that's going to be on the midterm 4? I would say, yeah, that most likely. I'm really into power reduction formulas. And for sure, there's going to be one of those on the final. Okay, I'm just warning you in advance. One of my pet peeves there. So I'm going to integrate 1 plus cos of 2 theta over 2. And I'm going to go pretty fast now. I don't like fractions, so pull the 2 out. That's a half. And then integrate. And because we're going between 0 and 2 pi, the sine term doesn't contribute anything because it's just 0 the whole way. So the only contributing term is going to be the theta here when it's 2 pi. Reduce this to lowest terms, and you get an exact answer, 1,023 square root of 2 pi fifths, which is approximately 909.0. And that could represent the mass of the surface, the cone, given a density function. Okay. Wow. So that concludes the second example here. That was a lot. Oh my gosh. What the heck here? Look how long this took us to do. I know. It took us like 2 pieces of paper. Yeah, I know. So what do you guys think? Do you want to try one? Okay, how about I'm going to give you one that's not in the course reader. I'm going to write it down for you, okay? And those of you watching at home, write this down and see what happens, okay? So here's an example. I'll call this example 3, not in your course reader. I'm just gonna hand it to you right now, and then I'll have you and a buddy try to figure it out. So here's what you're gonna do. You and a buddy are gonna evaluate this surface integral, f x, y, z, ds, where, now you need to be given some ingredients, I know. Your density function, f x, y, z, is x squared plus y squared plus z squared. Okay. And the surface S is given by z equals x plus y, so it is a plane. And it'll be bounded below by x squared plus y squared less than or equal to 1 in the first octant. So this portion of a circle, the region here, is in the first octant. Okay? So for those of you also watching at home, this z is also your capping surface, your little g. So now you know. Okay, you have all the ingredients there. So you and a buddy are going to evaluate this surface integral right here where you're given all the ingredients. All right. So this problem involves a lot of different steps, right? So they gave you a capping surface, which is really a portion of a plane, okay? And they wanted that portion of the plane in the first octant. So this in the first octant looks like a quarter of a circle. That's not a very nice circle here, like that. And so this is the region R that we are going to be integrating on when we convert the surface integral. How do we know it's a surface integral? It's got a big old S here, but we want to turn that S into an R to do a regular double integral that we can actually evaluate. I don't know how to evaluate this surface integral. There's too much stuff that needs to be figured out. Okay. So let's do this one by one. We've got little z here. Let's go get the partials. Ooh, that's pretty easy. It turns out the partials for x and y are both 1. So your surface area element is pretty easy. It's going to be a constant again. That doesn't always happen. But hey, if it does, I'm good. So what do we get? We end up with square root of 3 dA. Okay, so there's your surface area element. Don't lose sight of that like I did on that last problem a couple problems ago. I meant to do that, right? It's testing it. So what do we have now? So we're going to try to convert this surface integral into a regular double integral over the region. So this we just found out is square root of 3 dA. Nice. So then you're going to have your f x, y, z. But they said that was x squared plus y squared plus z squared. But wait a minute. You're not allowed to have a z in a double integral. So we need to replace the z with what? Our function, x plus y. So then what? So then we're going to have x squared plus y squared plus, still got the square root of 3. So you're going to have to FOIL this out. I know it's not pretty. Well, now remember, don't distribute the exponent because that's not legal mathematically. You know, that's not equal to x squared plus y squared. So if you FOIL it out, because you're going to go x plus y times itself, you'll get x squared plus 2xy plus y squared, but you also still have the first two terms here. You still have the square root of 3, and you still got this big mess. Okay, now what? You do have like terms, so these two x squared terms add together, and then the two y squared terms add together, and then you got this. So now it's time to recognize that we're going to have to convert to polar because our region here is conducive to that. And the theta is only going to go between 0 and pi halves since we're in the first quadrant. Okay, so when we start converting these first two terms, if I factor out a 2, are going to go r squared plus, this is not going to be very nice because you've got X replaced with R cos and Y replaced with R sine. And then don't forget your dA is R drd theta. And I'm going to move this square root of 3 way over in the front, just so I don't forget it this time. And then this term, let's clean it up a little bit. We'll combine the R factors. And now you're going to have to distribute this R before you even integrate. I know. So you're going to get 2R cubed plus 2R cubed cos theta sine theta. Okay. And so now when you integrate with respect to R, you're going to get what? Now what I'm going to do is I notice that 2R cubed is common to both of these terms. So if I factor it out, that should be okay, because this 1 plus cosine is really just a multiple when we're integrating with respect to R. So I'm just going to copy it down. And then the antiderivative of 2R cubed is what? R fourth over 2. And we'll go between 0 and 1. And that's just going to give me a half. Okay. And I'll put the half in the front. Now what? This is an easy Calc 1 problem. You should use U sub on this. What I do is I let U be sine and then du be cos. And then this looks like just u du. And so that is going to be u squared over 2. Page. Yeah. So then I'm going to have square root of 3 halves and then the antiderivative of 1 with respect to theta is theta. This is going to equal u squared, oops, just no more integral, u squared over 2, but that's going to be sine squared over 2. So you're going to have sine squared theta over 2 like that. And you're having your theta go between 0 and pi halves. Oh, okay. When you plug in 0 to either of these terms, both those terms are going to go to 0, but sine of pi halves is nice. It's 1. And when you square a 1, you still get 1. And so your final answer is, no, I didn't want to do that. Sorry, Microsoft Surface. So you're still having the square root of 3 halves, and then you have this pi halves plus a half. And what you could do is factor out the half, make it look a little prettier, not much. And there's your exact answer. Boy, that looks pretty weird. So to recap this surface integral, did anybody get this answer, by the way? Anybody get it? Close, maybe? Did some people get close to the answer? I'll check the chat.
So yeah, it is.
Okay, good. If you didn't, well, you just need more practice. That's all. Just need more practice. Okay. So that concludes surface integrals.